The question that I have is, could you show us how to solve a 3D cable problem? This is the three-dimensional cable problem that I have selected here. We have four cables, AB, AC, AD, and AE, that are holding a mass of 20 kilogram in space. The question is to determine the tensions in the cables. As in the previous two-dimensional examples, the first two steps are the same. First, we want to identify the particles to be analyzed, and in this particular case, you can see particles A and E are those particles. Then we want to complete the free body diagram for these particles, and I have done that on the main picture right here. At this point, hopefully we have done enough to recognize that the tension AE is exactly equal to the weight W. Obviously, that comes from the consideration of the equilibrium of particle E in the vertical direction, right? So in the next slide, I will only consider the free body diagram of particle A. And of course, we're going to assume that tension TAE is exactly equal to W. At this point, we are ready to apply the equilibrium equations to the free body diagram of particle A in order to solve for the unknown tensions TAB, TAC, TAD. The first step here is to express each of the four forces acting on the free body diagram of particle A in their vector form, in their component vector form. So let's do this one at a time. Let's take TAB first. We know that the line of action of TAB coincides with the x-axis, but in the opposite direction. We know the unit vector along the x-axis is little I, and therefore in the opposite direction it will be minus I, right? And therefore vector TAB would be simply minus times TAB, the magnitude of TAB, multiplied by the unit vector little I. The line AD, however, is a truly three-dimensional line. So we need to use one of the three methods we talked about before in order to represent that tension TAD in a vector form. Remember the three methods, right? The projection method, the direction angle method, and the position vector method, right? Out of the three, you can see this vector is set up for applying the projection method. First, I'm going to consider the right triangle ADF. And this angle is 30 degrees and this angle is 90 degrees. DF happens to be the opposite side to 30 degrees and therefore DF would be equal to TAD sine 30 and AF would be TAD cosine 30. And then we take AF and consider this right triangle AFG and recognize that this is 40 degrees, this is 90 degrees, and therefore GF would be AF sine 40, AG would be AF cosine 40, right? So the lengths of these three sides, DF, AG, and GF, are the components that we are looking for, right? But of course, we have to put appropriate signs with them. Now here we see that the x component is going to be a negative term and the y and the z components are the positive terms in that equation. So you simplify this a little bit and we get this for the vector TAD. We see that the line AC is set up for using the direction angle method. We are given the angles between the line AC and the x, y, z coordinate axes. The vector TAC then is this, and you simplify that, we get this. We also want to put this tension, which is equal to the weight in its vector form, so that will be 196.2 K with the minus sign in front of that. The mass is 20 kilogram and therefore the weight is 20 times 9.81 Newton, so that will be 196.2 Newton. The direction is vertically down and therefore I have a negative sign in front of this. So that's it. We have expressed all four of the forces acting on the free body diagram of particle A in their component vector forms. Now let's go ahead and apply the equilibrium equations. Here's a summary of what we did in the earlier slide, the vector forms of the four forces. These are the three equilibrium equations. Sum of the forces in the x direction must be equal to 0. Sum of the forces in the y direction must be equal to 0. Sum of the forces in the z direction must be equal to 0. The sum of the forces in the x direction equals the sum of the x component of each of the four forces. The x component of these forces are minus TAB, minus 0.557 TAD, 0.5 TAC, and that's it. And those three must add up to 0. And you obtain these two equations in a similar fashion. Now we are ready to solve these equations simultaneously in order to find the three unknowns in the equations. But we note that there is a particularly simple structure to these equations, which is that these last two equations only have two unknowns in them. And therefore we can use these first to find these two unknowns and then go back to equation number 1 in order to find the third unknown, which is TAB, right? So this is what I'm going to do. I'm going to find TAD from equation number 2. Substitute that into equation number 3, right? Then equation number 3 will be just in terms of TAC. So we can go ahead and find that. Then we go back and apply that to this equation to find TAD. Then we go back to equation number 1. So here are the details. Very easy to follow. I'll let you follow. So finally, I get these numbers. TAC is 181 Newton. TAD is 136.5 Newton. TAB is 14.5 Newton. We note that they are all positive numbers and therefore the forces in these cables are actually tension, the way they are supposed to be.